So we proceed with the rock classification. Yesterday we were talking about the kind of investigation you have to do for tunnel construction. But now the part of the investigation, then you need to, once you assess the rocks, and you need to be able to classify, and the report that you are saying that has to be useful to the other people. For example, after the assessment, then you grade the rock and say this rock is scored maybe 70, and that this kind of report is useful, has to make sense to the other people who are probably are not tunnel engineers, so that when he sees a value of 70, he has an idea. They have an idea of what kind of rock precisely are we talking about. And also the issue of training, because these are fairly technical things, so the other people who are not well versed in this area also have to be trained, such that whenever you're communicating in terms of the terminology, then you mean the same, they understand fairly what we are talking about. So rock types are classified according to their origin and physical characteristics as sedimentary, igneous, or metamorphic. This is, you can now see why you are required to study a bit of geology in civil engineering. So as given in the tables that have been indicated, so terminology used to describe intact rock for strength and weathering are given in the tables as shown. The importance of geology gains even more prominence in rock classification. So for you to be able to be well versed with these classifications, you need to have a bit of background in geology. So since many rock formations seem to pose similar tunneling problems, it is important to describe and evaluate the stratigraphy of rock, since many tunneling problems. So these are the tables that shows you the terminology of how to describe the rock, the words, let's say, and the maybe the texture. So this is the first one is for the table 4.7 is for sedimentary classification, 4.8 is for igneous rock, and 4.9 is for metamorphic rocks. So this other table is showing you the strength, basically how to describe. So if you talk about soft, the strength designation extremely soft, the strength designation is R0, and the range of unconfined compressive strength is between 28 to 100, and you can indent with a thumbnail. So this is a very soft rock that if you imagine that you can indent with the rock thumb. And please note the unconfined compressive strengths are in pounds per square inch. I'll show you. So for very low strength are 100 to 1,000. Crumbles under fine blows with a point geology peaks can be peeled by a pocket knife, breakable by finger pressure with difficulty. So a little bit more harder than the extremely soft, but still a very, very weak rock. Low strength are between 1,000 to 4,000 psi. can be peeled by a pocket knife with difficulty. Shallow indentation made by firm blows of geology pick craters under a point impact. Moderate strength are 3,000 to 8,000. Cannot be scraped or peeled by pocket knife. Specimen can be fractured with a single firm blow of geology hammer and will develop smooth pit or dent under point impact. Medium high strength are for between 8,000 to 16,000. Specimen requires so between 8,000 now to 16,000, we're talking about between 50 to 100 MPa in terms of MPa. And then a specimen requires more than one blow with a geology hammer, and requires more than one with a geology hammer to fracture it. Explosives, dents or pits, and the geology hammer point impact. And so strength are 5. This is 16,000 to 32,000 psi. That's actually between 100, about 110 to 20, 110 to 220 MPa. So if you talk about MPa, R6 is above 220 MPa. So that's very good rock. So for the high strength specimen requires many blows of geology hammer structure. It does not indent. Specimen for the very high strength the specimen can only be chipped by a geology pick. So these are kind of descriptive ways that you don't need any technical knowledge. So when you say moderate strength, everyone in the team needs to have an idea of the range of strength and the possible characteristics of this kind of soil. So again, descriptive terminology for the rate. Also, you have to assess weathering, because obviously the nature or the extent of weathering has something to do with the influence of strength. So fresh W1, no visible sign of rock material weathering, perhaps slight discoloration on major discontinuity surfaces. Slightly weathered W2, discoloration indicates weathering of rock material and discontinuity surfaces. All the rock materials may be discolored by weathering and may be somewhat weaker than its fresh condition. A moderately weathered W3, less than half of the rock material is decomposed and or is integrated into soil. A fresh or discolored rock is present either as a discontinuous framework or as core stones. Highly weathered W4, more than half of this rock material is decomposed and or disintegrated into soil. Fresh or discolored rock is present either as discontinuous framework or as core stones. Completely weathered W5, all rock materials is decomposed and disintegrated to soil. The original mass structure is still largely intact. Residual soil, so W6, all rock material is converted to soil. The mass structure and material fabric are destroyed. There's a large scale change in volume. Large change in volume, but the soil has not been significantly transported. So these are terminology for describing different weathering or degrees of weathering. So tidal problems are governed by geology. The one might begin to predict the potential for some types of ground behavior just on the basis of geologic formation. For instance, limestone formations frequently have solution joints or even karst features. Also, basalt formations have distinctive cooling joints and are susceptible to lava tubes whenever indicated geology is present. Such features may be expected. Potential effect on tunneling may be expected in the above cases. This might be a potential for large water inflow. So, of course, we know that limestone is susceptible to the solution being dissolved by acidic rain. I think you know this. So because of this, the you expect, if for example you know that the material you're working in is acidic rain, then you know what to expect. So let me, if I could find somewhere to write. Okay, I can write here. So for example, you know that limestone is calcium carbonate. So first, the issue is water, and this is why people are concerned about environmental pollution, because when rain encounters carbon dioxide, CO2, we get acidic rain, which is nothing but carbonic acid. Okay, in chemistry we are told this is not equal, so maybe use an arrow. And then, so this is the first part. So the water reacts or dissolves, carbon dioxide dissolves in acidic rain because we have a lot of it in the environment to form acidic rain. So when acidic rain encounters the soil, limestone is basically not the soil, I mean the limestone is basically plus calcium carbonate and then we get calcium oxide plus water plus carbon dioxide. So this is why you see formations of where we have calcium carbonate, there are caves, a lot of caves. I don't know if some of you come from Mombasa. The places like is it Marafa in Kilifi? There's a cave there called the Devil's Kitchen, and in somewhere around why do I forget this place? There's Kisiton Punguta National Park. Of course, the park is inside is in Watamu, is in Watamu Island, beyond Watamu Island, but the headquarters of the park is in mainland. Around there, Shimoni Cave, I think. Yes, I think Shimoni. Around Watamu there, the headquarters of Watamu Marine National Park. There's a cave there, and there's also the Devil's Kitchen in Kilifi. So this is in South Coast. and then there's the devil's kitchen. So this is just to demonstrate to you the effects of limestone. So if you are going to do your tunnel in such areas, then you can anticipate this kind of behavior. This is the point. Now, differences between soil and rock behavior. Actually, the other issue is the soil and rock do not behave in the same way. The rock is a little bit more complex because rocks are affected by many things. For example, discontinuities. They are expected by stratification. All the same issues affect. Okay, simply put, for example, you can sample the soil, and if the sampling was done in a very representative way, then the result from the lab could be reasonably, of course, within certain limits, assumed to be represent the in situ behavior. However, for rock, the behavior of intact rock is different from what you call a rock mass. Rock mass is like, because the mass of this rock could consist of many other things, because when you sample, probably you just sample a limited area. So because the rock is one continuous, first you check whether it's continuous. So if there are discontinuities, those will affect the behavior. So all these issues have to be considered. So rock mass descriptions are even more complex than soils. Aside from the obvious greater strength of the intact rock, the major difference in the behavior of rock from that of soil is that the dominant effect of anisotropy. So anisotropy affects rocks has a very strong influence in the rock behavior, or other discontinuities, like I've said. So these continuities range from texture or fabric in the rock, such as schistose foliation, up to major faults in the rock. Now, attention to the details of jointing is extremely important for rock tunnels classification. So just to so if this is your, let me go back to where I can draw probably something you can see clearly. So for example, here, this is your rock, and you create a tunnel here, and the rocks have some foliation, not foliation, but orientations like this. Maybe this is the rock, this is the way, you know. You can see within this affects, because once you create this hole here, this is a line of weakness. The stratification layers, these are lines of weakness. So they will affect the ease with which the tunnel might fail, because once you create a line of weakness here, and the rocks are jointed this way, most likely this part will slide into the space that you're trying to create, and you won't have your tunnel anymore. So all these things affect the behavior of rock. So like we said, that anisotropy has very strong influence on the behavior of rock in comparison so anisotropy influences the behavior of rocks strongly more than the influence on in soil. So attention to the details of jointing is extremely important in rock tunnels. Classification for joint spacing for joint roughness are given in some table I will show you later. The joints and the interaction between the various joint sets play dominant role in the kinematic behavior of rock masses. Now you will see later that when classifying the rocks, great attention is paid to the jointing because as I've told you, anisotropy plays very important role. Now when you take a sample to the lab to test, you may just take a limited area and if the size, depending on the size, if the size doesn't capture the rock discontinuities or rock anisotropy, then the strength you are going to measure in the lab is not going to be representative of the in situ behavior, and this is because the rock might be intact, the individual blocks of the rocks might be intact, but the overall behavior in comparison, in conjunction with the rest. This is why the behavior of rock mass is very important. What is this thing we call rock mass is not an isolated block of rock, because the isolated block of rock might be uniform, might have good strength, but how does this rock behave in conjunction with the entire rock mass, so different blocks forming. So these rocks are as strong as the joints, are the weakest joints. So in the rock classification, a lot of detail is paid, a lot of attention is paid to the joint, the nature of the joint, the distances, the spaces. Actually, most of the marks I told you yesterday that we are going to award marks between 0 to 100 in one of the classification systems. And while awarding these marks, you pay great attention to the detail, to the nature of the jointing, the sizes, the spacing, the contents, what fills up these joints, or the spacing, so all this will give you will add up to the eventual marks, to the eventual weighting of the classification of the soil. So great attention is paid to the detail, because anisotropy, or this kind of joint and spacing and all this have great influence on the rock mass behavior. So movement of rocks usually only takes place along the joints. I've said this, and this movement can only be along the plane defining the joint. So I hope this did not. The first this sliding can only happen along this joint. So once you create the open space, then if the sliding has to occur, the sliding can only happen on this joint. So that's why a great detail is paid to the joints. In other words, failure is imminent or most likely to occur along the joint. Further, the presence of joint drastically changes rock mass engineering properties. Joints determine the kinematic freedom of rock wedges have, and they dramatically affect the rock mass modulus. Further, they play a major role in the design and effectiveness of support on underground opening, say by rock walls. So Again, this is a key issue. I'm surprised that your syllabus is not demanding. I will check, but I am not sure that your syllabus asks you to design rock balls, because that's important, because this is one key issue. So if this is your that's your tunnel, and then there is a try to do a better tunnel, and this is your opening. So depending on the cracking around the cracks, if these are the cracks, this determine the for example, if the rock bolt now would be something like this, because you want to you remember the EDZ, the excavation damage zone. You remember what we were talking about yesterday, the EDZ. So you want the rock bolt to extend beyond the EDZ. So what you do is you dig some opening, and then you grout this end, and this has to go beyond the EDZ. That's a point. So again, the jointing, so you grout this end, one of the end is grouted, so that is anchored there, and you put some nuts at the wall of the tunnel. And so this is the layout. So this, the cracking, as you've seen, or the discontinuities determine the rock how the design of rock balls will happen. So that's what we're trying to say. And then those rock balls must go beyond, must be able to anchor themselves in a solid ground. The place where they are anchored has to be sound rock, such that the rock bolt extends beyond the broken the EDZ, the excavation damage zone. So this is a grout. We use grout to anchor the rock bolts. So these are the rock bolts. Rock bolts. So it has a lot of influence, and I think one of the courses you need to that is important. One of the requirements is you should be able to design rock bolts in this course. Check to your syllabus, maybe it's not there, but we may need to recommend that. Yeah, so just a minute. Usually take space along the joints, and yeah, excuse me. So yeah, actually, yeah, that's what I've said. Further, they play a major role in the design effectiveness of the support of the underground opening, say by rock balls. The significance of discontinuities in the rock mass is that They have an enormous effect on the engineering properties of the rock mass, and therein lies the great difference in approach necessary when comparing soil behavior with rock behavior. An undisturbed sample of soil taken from a core boring can often, but not always, I think I said this before, be considered representative of the soil mass and strength test values or any other engineering property. Values obtained on such samples are frequently attributed to the soil mass. In rock, even more than in soil, clear distinction must be made between the engineering properties of intact rock, I said this, the individual block of rock that you have tested, and the engineering properties of the rock mass, which include effects of discontinuities. I think I've said this, and this is why in the classification great attention is paid to the detail of the joints, the nature, the spacing, because the more than the property of intact rock, the entire behavior of rock mass is more influenced by the effect of discontinuities, strongly influenced by the effect of discontinuity. So size effects are important to rock tunnel projects. An intact rock sample from a core boring suitable for testing most likely does not have discontinuities that govern the behavior of the whole rock mass. So what we are saying, when you're sampling, the sampling may be very limited because you can only sample a limited diameter, and the properties of rock vary both vertically and horizontally. So if you just take a limited diameter, you may not capture the discontinuities that appear horizontally, and also even when you're sampling vertically, there's depth. You are limited with how much depth, how far, how much deep, or the height of the sample that you can collect is limited. So these are things that have to be factors that have to be considered. So an intact rock sample from a core boring suitable for testing most likely does not have the discontinuities that govern the behavior of the whole rock mass. Accordingly, the intact rock properties are generally only an upper bound of the likely behavior of the rock mass. So again, when you're interpreting the data from the intact rock from the laboratory, this is just an upper bound, we say, because this is the property of an individual. So this is like the maximum value you can, but you need to be aware that the actual behavior or the actual strength might be less than what you have measured from the lab. So this same relationship of the size of any tested zone to the scale of discontinuities must be understood. So the scale effect, in a nutshell, you're saying, must be understood during site characterization to ensure that the test results are not used incorrectly. Yeah. So once the lab test, you also have to understand the limitation of the application, and you have to know how to interpolate or interpret the data correctly, because of the effects I think we have elucidated. So this same relationship of the size of any tested zone to the scale of discontinuities must be understood during the site characterization to assure the test results are not used incorrectly. For instance, so the values tested in the lab have to be modified in line or to take care of the potential defects or discontinuities likely to be encountered inside. So at 3 feet, this is 3 feet is like 1 meter diameter plate. A load test may give representative results if the average spacing of discontinuities a few inches, but not if the average spacing is greater than 1.5 feet, is about 0.5 a meter. Similarly, a 10 feet diameter tunnel may behave well in a certain jointed rock, while 30 feet diameter in the same rock may experience difficulties. A great number of joints intersect the larger opening with greater chance for favorable orientation relative to a tunnel boundary and great kinematic freedom. This is just what I was saying. The size is important. I deleted this anyway. This is the same. Oh no, I think there's another. Yeah, this drawing. I can use this drawing to get my point across. So if this is your tunnel, assume this is your tunnel. No, may not be. Okay, maybe misleading. So I will try to draw here. And this is your tunnel and their orientation. So the size is important, because if the soil is oriented this way, not the soil, so the rock is stratified this way, let's say. So the small diameter, because the worst case scenario is you do not want the stratification to be this way, because that will mean that please record your attendance. I don't know what happened. There seems to be some issue. Record your attendance on the. Do it again, because it appears the maybe some internet problem. I have no idea. Okay. So this behavior okay, I think the maybe an internet issue. Yeah, okay. So the worst case scenario is that the tunnels align, and when this stratification align, because you'd prefer this, you'd prefer alignment to some angle, so that there is no way the rock mass can just slide down. So the size also the size increases the chances of better orientation. So if you have a smaller size diameter, so it probably you don't have direct the opening directly facing the orientation, such that once you create unload, then the potential for slide is obvious. So if there is some angle, if there is some orientation to some angle, it increases the chances that your tunnel will be stable. That's the point. So the size effect, basically in a nutshell, we talk about here the size effect. Yeah, so here we're talking about the size effect. So larger opening with greater chance of a favorable jointing orientation relative to the tunnel boundary and greater kinematic freedom. So rock characterization must address the inherent anisotropy of rock and the consequent strong directionality of any engineering properties. This is true not only in the small scale where the fabric in the intact rock samples such as foliation makes the rock anisotropic, but also in the larger scale where the joints and shear zones and faults make the rock mass behave anisotropically as well. So yeah. Oh my god. And shear zones have or faults make the rock mass behave anisotropically or directionally. So the joints in the rock make the rock mass behave like a jigsaw puzzle. Interlocking and the interaction of rock blocks place certain constants on kinematics of movements of any mass of rock in response to external forces, including those causing the excavation of a tunnel, caused by the excavation of a tunnel. So and let me try to draw here for your benefit. So what you are saying is, if this is the rock mass, and most likely this is so if you have several blocks like this, because you wouldn't know how so say the joints are like this, and then you have another rock block. So you can see that if you try to shear this rock, this is block 1 and this is block 2. So if you try to apply a force there and a force there, the blocks 1 and 2 behave like a jigsaw puzzle, and there is some interlock, so that it's not easy to move the rock block. In fact, this is why we say that the behavior of rock is more influenced by the joint behavior. So that's the point. So shear zones are persistent through growing discontinuities, interrupt interlocking effects. Yes, so dramatically changing the behavior of rock. See the figure 4.5. In situ, stresses both high and low play an important role in behavior of jointed rock system. Many tunnels have experienced considerable difficulties, particularly at potholes or topographic lows, where the stresses may be unusually low as the result of stress relaxation during valley erosion. Such cases result in open joints that carry water and are difficult to support in a tunnel heading. So figure 4.5. Yeah, so this is just showing the shear zone that interrupts the interrupts the interlocking effect. So shear, the interlocking effect that I have just explained is important to keep the stability, so that the shear, it's difficult to shear the or for the rock to slide. But if there is a shear zone, then it diminishes the interlocking effect, so that it's very easy for the sample to, for the rock block to slide. As you can see on this, in this diagram, you can see now the danger also. When you sample an intact rock, you may not be able to, you can see the discontinuities, but in sampling you might not be able to capture the discontinuities. So this is why we are saying the behavior of the tested rock in the lab should be taken only as a higher and an upper bound, rather than the actual. You need to understand that this is, if this the actual behavior is more influenced by anisotropy on joints, and the values obtained from the lab have to be modified to be used to be applied in situ. So finally, the permeability of rock mass is also dramatically affected, of course, by discontinuities. You can imagine, if there are discontinuities, water would only tend to flow around the cracks, the discontinuities, I should say, or the imperfections. So sometimes a discontinuity such as a shear zone may be permeable and result in considerable water flow. So in fact, this causes even a problem. There is no agreement on how to define permeability of the rock mass, because if for example one discontinuity is just half or a few fractions of a millimeter, and there is another opening that is 2 millimeter wide and another one 5 millimeter wide, all these things will have different will allow different amounts of water to pass through. So if you are going to determine the effective permeability of rock mass, what is the basis upon which you are going to do this? So even getting a representative or permeability is there's no universal agreement on how to do this. So these are some of the challenges posed by discontinuities. So like I was saying, however, sometimes the shear zone may be impermeable and act as a dam, holding back abundant water on the other side, and high heads that will encounter suddenly upon tunneling through the zone. So sometimes water is accumulated in the shear zone and under very high head. So when you are doing the tunneling, so the point you at the time you break into the place that is holding the water, then water will come crashing at very high speeds at high pressure. So this is some of the issues. So even the concept of using effective permeability coefficient is challenged in rocks, yeah, because we like when we are designing, we like nice values, like say, okay, the permeability of this rock mass is so much, but you can see with all this the possible different sizes of joints, the effect of the shear zone. The joints might have different sizes. The amount of water passing through these joints might vary. So when you get an effective permeability, it may not necessarily represent the actual in situ condition. So even then, in such a situation, if you have such a situation, even then when we talk about effective permeability, it's in doubt. You really have to think on what are the implications. So the effective permeability of the rock mass is governed by discontinuities or other defects in the rock rather than permeability of the intact rock. Yes, because in fact permeability is supposed to measure the material rather than the discontinuities, but you see the rock mass is the material itself, which is somewhat permeable, but it's more influenced by the discontinuities. So not only is this is the permeability of a rock mass anisotropic as it is in soil, but groundwater may pass easily through some joints or even some portions of a same joint, but not through other faces. Yeah. So even for the same joint, some water may pass easily through certain portions, and in certain portions there is a difficulty depending on what has filled the joint. So to get a representative way to describe this flow scenario might be challenging. So I think we can take a break for 10 minutes, and we resume the class. Class rep, you need to explain why the class is poorly attended. Let's resume at I think 11:30 is good. Okay. So there are some classification methods that we need to study. So this is like the unified classification system, but for rocks, the unified classification system for the soils. So in order to provide a degree of organization and standardization to seemingly complex and confusing masses of field data, the concept of mass classification was developed by engineers. This classification system gives the geotechnical engineer or geologist method of assessing the relative importance of each rock parameter or a geologic feature of each condition contained in the given classification system that is being used. They are in a sense an extension of the concept of using soil mechanics, the unified classification system, and forerunner of what are the now called expert system. This is from Barton in 1988. Barton 1988 states that QA system is essentially a weighing process in which the positive and negative aspects of rock masses are assessed. This is a good description of what all rock mass classification systems adopt. In practice, rock classification systems are generally used to predict behavior by applying the concept to data obtained by logging rock core and logging rock outcrops. None of the systems is perfect, and it may be necessary to adjust or fine-tune the particular rock classification system to fit at the type of rock encountered and to account more properly for special behavior of rock condition being characterized. Further, during the construction of the tunnel, the exposed rock can be logged in to obtain input data which can be used to calibrate rock mass classification system for use on future channels in the same geologic environment. So what we are saying is that we've seen a lot of factors affect the behavior of rock, and we are trying to find a simple direct way or a uniform way to so that there is a common basis for understanding. However, they are not perfect. There are some things that are difficult to cater for. So these are we can say work in progress. It based on experience. There's a lot that still requires to be improved. This is the point. So in a sense, every experience is important. Every past experience is important. So these are basis for assessment, current assessment, but with availability of more data, then we are able to fine-tune these systems and use them. So the history of development. Terzaghi in 1946 developed a method of classifying rock mass types could be used to describe and evaluate rock load on the steel supports. Although this classification is decades old, the rock mass terms and description coined by Terzaghi are still useful in communicating about the behavior of rock masses. The basic descriptions are given in table 4.4-13. In practice, there are no sharp boundaries between these rock categories, and the properties of rock indicated by each one of these terms can vary between wide limits. Lofa in 58 developed a stand-up time classification method that correlated stand-up time of and supported spans with rock mass quality. Many others throughout the world have contributed to the development of development development of rock classifications. So this is the table by Terzaghi. We talk about intact rock, stratified rock, blocky or semi-system, crushed, squeezed, swelling rock, and so on and so forth. And these have something to do with the level of weathering that we've already talked about. So, and even today the description, the descriptive words we use do not veer off this foundation given to us by Terzaghi. So there is what we call rock designation quality. In fact, this is useful even today. In the mid-1960s, Dr. Don U. Dewey of the University of Illinois developed and improved a method of logging rock core to calculate modified core recovery percentage called the rock quality designation. RQD is an essential simple measurement of the percentage of good rock in core on intact pieces of 4 inches or more in length, and has been found to have a much better correlation to actual behavior of rock than the standard percent rock core recovery. So there are two things, and I think these are useful even to date. So it correctly reflects the fact that a rock mass that is so fractured or weathered that there are more pieces of sound rock longer than 4 inches will also behave poorly during construction. It was the first time that engineering behavior rock mass could be estimated. Subsequently, could be estimated from a simple parameter obtained from logging. So subsequently, the rock mass classification systems were developed that provided quantitative numerical values because you can see it doesn't just give us some description, but in engineers we like some values that have specific meanings that we can give us a good meaning. We can get can give us a value with some specific meaning is something useful. So conditions such as groundwater flow, inflow, the joint spacing, orientation and condition, and intact rock strength, rock stress, etc., whose combined effect were previously described in more qualitative terms. So like yeah, we've said this that previously you can see the values given by design were more qualitative, but we prefer some specific figures that have some specific meaning. So Wickham, Chapman, and Skinner, these researchers 72, developed a numerical system that rates and weights record rock mass parameters to correlate rock mass quality and excavation dimension ground support. As this is in 1988, this researcher. RQD gained immediate acceptance, is now very common. In fact, is the basic parameter used in two most widely used comprehensive rock systems that have developed in the last couple of decades. We have methods called Benoist rock mass qualification, rock mass rating RMR, and there's another one we call the Q system. Those are the major classification methods. We're going to study them in detail, but in fact they are based on the RQD system, so the rock quality designate. However, the RQD could not have some limitations. For these reasons, then this RMR and the Q system have some improvements to counter for things that RQD could not cover. However, this is useful even now and is based on the fact that if you cannot recover when you're drilling, if you cannot recover cores that have lengths more than 4 inches, 4 inches is 100 centimeters. So if you can recover rocks that can stand continuously for 100 centimeters, then this is a reasonably good rock. However, if you cannot recover these, then that shows that the quality of rock that you're talking about. So on the basis of this, that either you can recover lengths of 4 inches or not, then there is some percentage you calculate. So for example, if you have recovered one meter, for example, then you count the number of pieces that are 100 centimeters or more. So the percentages of recovered cores that can stand for 100, that are 100 centimeter long, and now that is what we call the RQD. So versus the number of recovered cores that are 100 centimeters long versus the number of cores that are less than 100 centimeters long. So this ratio is what is given as a percentage as the RQD rock quality designate. Of course, the higher the value, the higher the quality of rock. I think is very common in so I'll show you some report for a client, maybe he, I think is here. Now these are yeah, so you can see you can see here that in the logging you can see there in the logging we have the total core recovery, for example 67, RQD is 20%. So this is what I'm trying to tell you. Even today, in fact, when you're doing site investigation in rock, this is a very important parameter that has to be logged by the when you're doing excavation. So the common worldwide because it can give some figures, and RQD is the basic parameter used in the most widely okay, so we've said this already. The subsequently so actually RQD did not replace the traditional so you can see that total core recovery, the report I've just shown you shows the total core recovery percentage. So both are usually recorded. I think I've shown you that's the point. RQD did not replace the total core recovery. Total core recovery is based on the how intact the length of the intact core that you can recover versus the length of an intact core. So they are related, but RQDs speak on the length of each. So for if you for example consider 1 meter, how many 4 inches lengths can you recover, and those less than 4 inches. Now total core recovery is in one meter you have recovered maybe 8 centimeters, so that the total core recovery would be 80%. But RQD was found to be give good representation of the actual behavior. So in on-site, they are reported both RQD and total core recovery method. So the two percentages tell a lot about the quality of the rock and its likely behavior during construction. As simple as RQD is, it still requires a full understanding of how to drill and how to measure and count the pieces in Quran. The minimum standards for RQD as follows. Good drilling techniques are essential. This is the standard sizes, standard core recovery sizes. Drilled with double tube core barrel, generally not greater than 5 meters. 5 meter is about 1.5 meters. 5 feet is about 1.5 meter. Okay, count only pieces of core that are at least 4 inches long or 100 centimeters. Count only pieces of core that are hard and sound. So hard and sound, but are 4 inches long. Of course, if the drilling action cannot break the rock, and you find that it can still stand for 4 inches, then obviously it's hard and sound. And the so from drilling, the RQD in the field, this log RQD in the field immediately after recovery before any deterioration. So many things can happen. Rain, heat can make some samples expand and break and continue. So once you recover the core, you make these observations immediately without the external influence. So core diameter is larger and slightly smaller in diameter than that standard size of 2.155 inch can be used, but then the smaller BX and BQ size. Now these are just the designation of the course, the core cutter that is used to sample this. BQ sizes are not recommended because of greater potential for core breakage and loss. The widely used NX and NQ size 1.875 inches wireline cores are used extensively for RQD determinations and are the optimal core sizes. There are strict rules and procedures for determination of RQD. An example of an RQD core logging procedure is illustrated in figure 4.6. So figure 4.6 I'm going to shows you exactly how to rate the length, how to count, and gives you some actual reference. So core length should be measured along the central line of the core breakage caused by drilling or handling, as evidenced by a fresh rough so sometimes, in fact, the core breakage caused by drilling or handling, as evidenced by rough rough edges, showing rough surfaces should be ignored with the pieces fitted together as set together and counted as one piece. So because you're using machine, sometimes there might be some breakage. If you're sure that the breakage has been caused by the machine, the drilling action, then you should count that as intact. However, if in doubt, then you should assume that it has been broken by the natural process, in which case the result would be conservative but safe. So with respect to soundness of the core, as this ISRM is a standard, international standard for rock mechanics, whether in grades. ISRM means International Standard for Rock Mechanics. Whether in grades 1 and 2 are counted. Grade 3 moderately weather is counted, but given an asterisk to indicate that is not quite sound. So this is showing you how to do the RQD precisely. So I think that is a good example showing you how the percentages are computed. So we are considering the sum of lengths that are greater than 4 inches over. So we only consider the ones that are greater than 4 inches. So in this case, you can see this is greater than 4 inches. L38, L17. So these are 1, 2, 3, 4. So you add up those lengths and then divide by the overall length, and you can see how the value has been achieved. So grades 4 and 5 rough, highly and completely weathered respectively are not counted. This is an important aspect that is often overlooked. Details of RQD's history and of its correct use are given by Dora in that reference. There are many useful correlations between RQD and other parameters or descriptions of behavior. The basic classification comparing RQD with qualitative rock quality and timeless description of rock is given in the table I will show you. RQD is very useful, but like the all index properties, RQD has limitations. In particular, it does not take into account joint orientation, which is very important. In fact, I have said most of the methods the two main classification methods that we're going to use are based on RQD. However, they are going to lay a lot of emphasis on the nature of joint and the orientation. So you will get a feeling that the joint is very important. The surface, what fills the joint, the spacing. So some of its advantages are as shown. So the tables, I'll show you the table 4.14. So this is how to some descriptive words. So if you get an RQD of 90 to 100%, that's intact rock. Excellent. Good, between 75 to 90. Massive, moderately jointed. Fair, 50 to 75, blocky and semi. Poor. You can see these are the descriptive words from Tezagi as well. So the RQD added the fact that you can add some figures you can attach to these words. Tezagi just gave some description. Now the RQD system or DERE added some values to some words, not words but some figures, so that we have we can attach the figures to the behavior. Now these are some of the advantages: a simple, repeatable, inexpensive, internationally it has international acceptance, and dimensional, quantitative, correlates to modulus and accounts for weathering. So these are the limitations, and these are the reasons for which other methods have been proposed. So does not account for joint orientation, does not account for joint continuity or persistence, ignores interlocking of rock blocks, ignores block sizes, ignores external forces like groundwater, ignores a nature of joint surface and filling, does not account for geology. So for this reason, Beniowski came up with the classification. This, I think I had mentioned this before, the RMR system, one of the most famous methods. So this was introduced in 1973. The RMR geomechanics classification system, which provides a valuable weighted parameter system that accounts for the relative effects of 6 rock mass parameters. Based on a careful analysis of the behavior of numerous rock tunnels in different kinds of rock, Beniowski has given each parameter relative importance in the RMR weighted point system as shown. So in the RMR system, we take care of so many things. RQD is one of them, right? A jointing, is there water, any presence of water, the size of the joints, the nature, what fills the joints. So each of these have marks. Maybe I better show you from here. Jesus Christ, the end of the class, but it appears the just send the messages again. I was saying the Beniaski system, the RMR, if you see the, I think it's better to explain here. So one of the parameters for the RMR system is the classification, the strength, and you can see the strength has a total max of 15, so very greater than 250. Do you remember the range that we were giving before? One of them I remember is 8,000 psi to 16,000. So Mimi agrees with this. Okay, so if a point load or for unconfined compressive strength is more than 250, you give a rating of 15. If point load is between 4 to 10, the unconfined compressive strength is around 250, you give 12. And so for this, this table is shown and is given in the notes. So for this is one. So the aspect of the strength is one where you award marks. Again, the RQD you can get. So if the RQD is between 90 to 100%, you give 20. 75 to 90, you give 17, and so on. So the first factor is the strength. The second one is RQD. Then the third is the spacing of the joint, as you can see, the joint set. So if it's a the joints are sparsely populated, more than 2 meters, that is 20. Now if the spacing are very close together, that means the rock is much weaker, and so you give a few marks. And again, there is the joint condition I've said. So you can see, apart from RQD and the uniaxial compressive strength, the rest of these things are now based on the joint. So the first is the joint spacing, which has 20 marks, and another one you can see now, the joint condition has 30 marks. So far the joints have 50 marks altogether. So the condition, if it's rough surface and limited extent and hard rock wall, then you give 30 maximum marks. Otherwise, depending on the different condition, the spacing, you can give from 30, 25, 20, and to 10. So at the end of the day, if you consider all these factors, then you add up and weigh, and you can get 80, 70, 50, or 10, and then you can say this rock is good or is fair. And also another condition is for if we have groundwater. So these are the ratings: 15, 10, 7, 4, and 0. So if it is dry, it's 15. It is damp, 10. If it is wet, 7. Dripping, and so on and so forth. And then the orientation, the joint orientation, you can see here you have to modify based on the joint orientation. If after you add and you get 80, and then you realize there is some orientation based on this marks, then you subtract. For example, after you score and you get 75, and then you realize there is some orientation which is not favorable, then you subtract -2 or unfavorable, or and so on and so forth. So at the end of the day, you have a grading which you can use to classify the rock. Now there is also so there is also some curve here. So once you determine these grades here, this is the grade 1, 2, 3, 4, 5. So very good rock, good rock, fair rock, poor rock, and so on. So once you do that, then there's what you call some level of fissuring. so depending on the porosity, you can see in this table, and then you can come to this table. In fact, so based on the porosity, you can say this rock is strongly fissured and category 3. Category 3, you know what that means. We have category 1 is 80 to 100, 81 to 100. Category 2 is scoring between 61 to 80. Category 3 is between 41 and 60. Category 4 is between 21 and 40. Category 5 is between 0 and 21. So you can say this one is poor, strongly fissured, poor and non-fissured, or poor, and so on and so forth. But most likely a non-fissured rock would be very good. So you can use this table as well, to this figure as well, to classify the rock. Now you can also convert the this is another system, the Q system. This is the formula. I'll show you this in the notes in detail. I'm just trying to give you an overview. So you can see we base this again on RQD, and these other factors of J. You can see how much prominence is given to the joint. So and then with some other factor there, and so these are these are have actual values depending on the nature of the jointing, the values of Jn and Ja and Jr, and also the SRF. So you can see at the end of the day, the Q system, this is the Q system, has some, is a little bit more wide than the RMR, because RMR rates between 0 to 100. The Q system rates between 0.01 to 1000 and is on a log scale, and the reason for this is because the variations in the nature of and strength of rock can be as varied as you can imagine. So this is the issue, to take care of very minuscule differences. So this is the basis. So to the note, so this is the same idea, in fact. So we say that the Beniaski has given relative importance to weighted system as shown to the 4.6. The entire table weighting points of RMR, the mechanical system Beniaski. Each of the 5 basic is evaluated parameter is evaluated given a numerical rating in accordance to 4.17. I think we'll see the tables in detail. The total points derived from the sum of the basic parameters are then adjusted according to table 4.17. So I think something is not right here. So some okay. So there are no extra ratings down there. Okay, fine. Just a minute. Yeah, I think something is not right. So to account for dipping, so the values in so let's make this put this to the next page for clarity. So the values are like I've shown. You add, and then eventually you account, you provide some factors that account for dipping and the joint, like I've said, continuities on the account of the effects of strike and dip joint. So this is what I'm trying to say. So we give some marks. Once you get the marks, you modify the marks based on other issues like the dip. The dip and the strike are the orientation. Dip is orientation in the vertical direction. Strike is orientation in the horizontal direction. That's all. So discontinuities on account of the effects of strike. So let's have dip of the account of discontinuities on account of the effects of the strike, and dip of joint discontinuities on the type of structure under consideration. The resulting total adjusted rating is the RMR of the rock mass under consideration, and the rock mass is classified into the rock mass according to table shown 4.18. Correlations from the numerous projects have enabled the above generic classification to be extended to predict broad ranges of rock mass behavior, such as ground behavior in unsupported openings, and support requirements such as rock bolt spacing, shotcrete, as well as estimates of rock mass modulus. Other parameters. Biliaski proposed that we relate the Young's modulus of the rock to the RMR system. So from the RMR, then you can know the Young's modulus of the soil. So since of the rock, sorry. Since an index property is used in making the calculation, the resulting value of the rock mass modulus should be considered to be no better than an index of the rock mass modulus, and thus only a rough estimate. Generally, projects that require a rock mass modulus in design will warrant the actual determination by borehole jack or large-scale in situ test. However, once several of these large-scale tests are conducted, a site-specific correlation between RMR and modulus of certain rock formation can be developed. Then an estimate of the variation of rock mass modulus throughout the site can be made inexpensively by using this site-specific correlation and the RMR obtained from borings exposure of rock in outcrops or examination. Adit are the horizontal borrow pits. I think we already talked about that. The pits, normally we dig pits vertically. Adits are horizontal observation pits. And these are the tables now for the point, how to adjust the points. So I think this table is put in the wrong place, because this table should come at the end once you apply. So here, this table should come here. Not exactly, anyway. So these are okay. These are the points. You can see all of them add up to 100. So if you have a rock and you want to classify, you look at the axial compressive strength, or there is another way we call point strength test. So based on the strength, we can say 15. So you can give a maximum of 15 if the strength is more than 250 MPa. If it's 100 or 50, you can see, so we can give maximum 15 to 12 to 10 to 8 to 7 and so on and so forth. Now for RQD, maximum of 20, depending on whether the RQD is 90 to 100, to 75 to 90 and so on. The specific. So once you add up all these marks, and then you adjust based on this orientation. If there is no orientation, you give 0. Alright, and at the end of the day, you get a rating like this. So you can say, okay, this is very good rock class 1 or class 2, class 3, class 4, and class 5. Now this is the matrix that we use. So for the uniaxial compressive strength, based on these are the strengths. So under what condition do you give 15? When the strength is very good. When the strength is in this range, you give 12. When the strength is in this range, you give 7. When the strength is in this range, you give 4. And this ranges you give 2, 1, 0, and so on forth. And then the RQD, when the percentage is 90 to 100, you give 20, 75. So that's the matrix, alright? And then the spacing of discontinuities, you give a maximum of 20. If the spacing is 0, 6 to 2, 15, and if the spacing is very small, you give a circular max. The condition, so these are the description, rough, and so on and so forth. You give from 30, 25. The ground floor condition, none, you give 0, of course. If there is some damp, you give 10, wet, and so on. So this is the matrix how to give find the max. So for example, in the exam you will be told the strength, then the joint condition, and all these things, and based on this table you should be able to award marks. And then there would be some information also about the orientation. So after you award the marks, you have to adjust as already been explained. So this is for the rock mass rating by Benoski. Now there's the Q system by Barton. I think I've already shown you this in the first part of this lecture, but just the details now. So again the Q system proposed by Barton in 1974. Benoski proposed his in 73. So and so this is the Q system by Barton. Barton was the first author, but there are 3 of them. So its background, basis, and the implementation are well described in this reference. Like all classification, the Q system provides tables that enable the user to assign numerical value for each of the Q system rating parameters depending on the condition of the rock mass with respect to each parameter. Barton's methodology for assigning the numerical ratings to the 6 parameters is given in table 4. I'm going to show you. To obtain the overall rock mass quality Q, the 6 parameters are combined in the following equation. Rock due to heavy squeezing, ground relationship between. Anyway, this is supposed to take care of because in the supposed to take care of what is called the stress condition. You will see there's a factor in that takes care of the condition, the stress condition. In fact, this is the equation. The equation. So you can see the Q system is the RQD, we said, based on JN, JR, JA, JW. JW is related to the water, the condition or the water condition in the joints. JN is related to the number of joints. JR and JA are some factors related to the condition of the joints, and SRF is a stress relief factor, and I'm surprised. This is So anyway, yeah, so this is what you are saying. I think this is important for you. So this is the Q system proposed by these authors, and again based on the RQD. So the equation is, why is the equation? Yeah, so we have to so I just repeat the equation here for you to see. Again, this is the Q, and we say that based on RQD, very important, the very first way of classification. And then the JN relates to the joint. So you can see we lay a lot of emphasis on the joint. All these factors 1, 2, 3, 4, 5 have something to do with the condition of the joint, and we say this is why we are saying that the joint and its condition have a lot of effect on the strength of the rock. So Jn is the number of joint sets. I've said this. Ja relates to the roughness of the joint. Ja relates to the wall rock condition and the filling material. Jw relates to the water flow condition of the rock, and SRF relates to the looseness and the stress conditions I've said. So the Q system seems to cater for the stress condition, something probably that was not taken care of by the RMR system. So the results in the overall rock mass rating Q having an extremely large range, approximately 0.01 to 1000. I've said this before. According to the Q system, the Q can accommodate the entire spectrum of rock mass conditions ranging from sound and jointed rock to heavy squeezing and ground. The relationship between Q and RQD is given. I think I've already given in the table. I'll show you. Now, the reason for this is to cater for a varied range of the rock conditions. So the implementation of the Q system is accomplished through correlating Q and an effective span. The effective span is Barton's method of applying risk, or what we call the safety factor, to application. It is obtained by dividing the actual span of the excavation support system. Guidelines for determining this is given in table 4.24. A lower excavation support ratio provides higher degree of safety. An ESR of 1 is used for civil works projects such as power stations, major road and railway tunnels, civil defense chambers, portals, intersections. For this case, the actual span is the effective span. An ESR ratio of 0.8 is used for underground facilities where sensitive machinery or people will be located. On the other hand, if excavation support ratio for temporary mine openings could be as high as 3 to 5. Figures on tables and then provided, of course. This is the nature of engineering. So this is the table that we're talking about. So not the table but the figure. So this span or distance over the effective support ratio, and then this is the rock mass quality based on the Q system, and the kind of support you need, and whether the rock is poor, extremely poor, and then the effective span that you can use. So actually this is a very useful table because for quick design or quick reference, based on the RQD value, then you can easily find effective. So this is actually a quick design reference table, so to speak. You can even design the length of the balls. You remember the rock balls I said, the length. So what we are talking about is and based on the kind of rock, you remember I said that's the, and you have to put rock bolt. So this is the length that we're talking about there. So this is like a good design reference, a quick reference for you, and I think a very good reference table for designers. So you can design your support requirements shown like any other rock mass classification system should be used with qualified geotechnical internal design with RAPTEN, of course, because to understand the interpretation, even the limitation of this figure, but it's quite useful as a quick reference guide, design guide. So actually, based on this table, you might be told to design a rock bolt or determine the rock bolt length or so if given a span or diameter or height of a tunnel and a ratio, excavation support ratio, and you know whether rock is poor, very poor, or fair, and the RQD system, you can be able, at least based on these figures, to determine the spacing of the bolt spacing, we should say. So this is the Q system, and these are the ranges of the values that we've talked about. So the number of joints, joint roughness, joint alteration, joint water conditions, stress reduction factor, and these are the matrix now to the specific conditions for the to give the ratings of 0. Okay, this is the same table that I've shown you here. These are the same things expressed differently here. So you can refer to the last two slides. In fact, this one, these slides, this group of slides. This group of slides is the same thing. So all those details is showing you how to assign the SRF or the JN or the JA. So this is basically a repeat of what is shown. But what I will tell you is, so this is where we are ending now part. So the exceptionally poor, the same idea with the rock mass rating system. So for these are exceptionally poor rocks between 0.01 to 0.1 is extremely poor, very poor, all the way to the exceptionally good. But this range is a little bit wider if you compare to the rock mass rating system. And this will encounter all manner of will be able to accommodate all the wide-ranging characteristics. And now these are details you can read for yourself. All what is represented in those tables can be summarized here. So how do you decide which value of JW to use, for example? These are the description: large, inflow, medium, washout, and all this. So you can assign these values. The stress reduction production condition. This is how to determine those values. And yeah, so that's for the water condition. And so this is also for the JN, the number of joints, the roughness or discontinuities, the what the JA, these are JA values, and the conditions for which you will decide which values to apply up to 20. And this is also how to apply the to convert one system, the Q system, into R system, or R system into the Q system, RMR system into the Q system. So the last two slides, what is shown in the last two slides is a summary of actually a summary of the tables, all these tables that you can see here, which you can read for yourself. Finally, what I'd say is this here. You can see a layout of poorly laid boring and proper boring, because you need to get as much information as possible. Now you can see the one that you're calling poorly bored is that there is a lot of anisotropy, and there are a lot of stratification. But you can see the, for example here, this pit is just dug in one material. So whoever is doing the excavation might assume that this is only consisting of one material, but as you can see, there's so much stratification. So if you do pits like this, this is for some. This is the same reason why you also need adits. Adits are kind of horizontal border pits, so that you can get as complete information, because these pits will only give you limited or the wrong impression of what is in this such condition. So in summary, the rock classification system, you have to consider the fact that joints have a very strong influence on the behavior. We had initially the rock quality designate RQD, then the total core recovery, then we have the Benoski RMR system, which we've described how it rates a rock from 0 to 100, and then now we have the Q system proposed by Barton, and this is gives values from 0.01 to 1000, and you can see how these values are being maintained. And also there's a reference design chart, I think very important figure 4.7, that will give you a quick design reference of how to design support based on the rock condition. So this table is quite important as well. So unless there's a question, we will stop here. And class rep, I think the class is poorly attended, and you people know that you should attend at least 75% of the classes. So I'm not sure what exactly is the reason for such poor attendance. Class rep? Class rep? Hello? Class rep? Anyone who can hear me, please respond. Hello?